Okay, we're still talking about dimensioning features. Let's talk about spot face now. So a spot face is a little bit different than a counterbore. When you're dimensioning a spot face, the diameter only applies to the flat surface. Okay, so that would be just a flat surface, doesn't include the radius. The minimum information would be the hole diameter and the spot face diameter. To control the depth of a spot face, you, kind of like a counterbore, you would dimension either the depth of the cut or the remaining material. Here's some examples of spot faces mentioned. Now, a spot face is just a little bit different. When I think of a spot face, I like this feature right here. What you have is a boss. Okay, let's say it was a forged boss or something like that, and you got this corner radius over here, and what you're trying to do is you're going to have a mounting hole drilled into this boss, and what you need is a flat surface for which the washer or the bolt face, holds the part down. So all you're trying to do with a spot face, and they're typically shallower than a countersink, is you're trying to provide a parallel surface to the mounting surface for which to mount a washer and a nut usually. And then you use the, it looks like a counterbore symbol, but you use SF for spot face. Now let's talk about limits of size tolerances. General tolerances in notes is acceptable. Okay, so you could have a drawing note that says, hey, all dimensions, tolerance is plus or minus 5. And then you can have tolerance specified on size dimensions. They could be limit dimensions, which is the min and max. They could be bilateral tolerances. They could be unilateral tolerances, or they can be single limit tolerances. So let's talk about those. Size tolerance limit dimensions. Okay, so specifies the minimum size and the maximum size. Maximum size is always shown above the minimum size. Okay, so these here are size tolerance limit dimensions. Okay, 0.999 is the maximum dimension, and 0.997 is the minimum dimension. And that's how the tolerance is specified. Plus or minus tolerances. Maybe bilateral or unilateral. So bilateral tolerances may be equal or unequal. Okay, so we got plus or minus tolerances here, +1 minus nothing, and in this case we have an equal bilateral tolerance over here, 250 plus or minus 2 thousandths. That's called a bilateral, an equal bilateral tolerance. Now compare that to a single limit tolerance. That is like a min dimension or a max dimension, something like that. Okay, and in this case here we got a radius, and the limit on the size is max, which means the radius can be anywhere from a sharp or no radius all the way up to a 30 thousandths maximum. And in this case over here, we're putting a minimum length dimension on a knurled feature. Okay, tolerances on angles. You can do limit dimensions, plus or minus tolerances, orientation tolerances, and then single limits on angles is not practical. Okay, here's some examples of angle tolerances. In this case here, we have a dimension, 0.3, 300 thousandths, that defines this land feature over here. And then from there, we have a 30-degree angle. So in this case, the tolerance on the 30 degree is a half of an angle, half of a degree. So this is what this means. We have the land feature over here is a min of 0.28, a maximum of 0.32, and then from there the angle starts off, and it could be from 29.5 degrees up to 30.5 degrees. That's one way to do it. This one over here, instead of putting a tolerance on the angle, we put a tolerance on the two flat dimensions, 50 thousandths and 30 thousandths. And this is what it means. Okay, so 50 thousandths plus or minus 20, the min is 0.48, max is 0.52, And then this is the same thing over here. And really, the tolerance on the angle becomes, hey, as long as this dimension fits in these two zones that's drawn here, it's good. That's how we dimension the angle. Now let's talk about calculation of size tolerances. Okay, so anytime you have some parts that fit together, like a wheel that fits on a shaft, for instance, you can classify the tolerances of the fits. And when I say tolerance of the fits, I mean that you have a shaft has an OD with a tolerance, and then you have a wheel that has an ID with a tolerance. And then these would be the classifications of fits. So RC is a running and sliding clearance fit. LC is a location clearance fit. LT is a location transition fit. LN is a location interference fit. And FN is a force fit. We touched upon this briefly in the last chapter. So to talk a little bit more about these fits, if we specify an RN, a running and sliding, that is a clearance fit, which means the wheel is always, the hole in the wheel is always bigger than the shaft. The parts will move freely on each other, and then there's 9 classes, and we're going to talk about those in a minute. LC is a location clearance fit. Again, it's a clearance fit. The parts always go together without interference. LT is a transition fit. Now, you can have, at some limits of the tolerance, you'll have interference. At the other limits, you'll have clearance. Okay. Whereas an LN is an interference fit. There will always be an interference between the wheel and the hub. And then FN is the force fits. Okay, so if we were to look at these from top to bottom here, these provides the most clearance. This one provides least clearance. Okay, so calculating size limits using standard tables. Okay, so the function of the parts is always considered when you're choosing what kind of fit to use for parts. Description and general applications provided. You got to determine the class of fit, and then you need to determine the tolerance values. And then the tolerance is proportional to the size of the feature. And we do this using these limit calculation tables, and I'll give you an example on how to do that. So how you do that is you select the class of the fit, you select the category of the fit from the class, you find the appropriate tolerance table, you locate what your nominal size is in the table, and then you calculate the tolerances. We've seen this before in other classes. Let's talk a little bit about maximum material condition. Maximum material condition exists when the dimension feature of size is produced at the limit of the size tolerance. Okay, so for holes, maximum material condition when the hole is at its smallest tolerance size. And then for a shaft, MMC is when the shaft is at its largest permitted size. In GD&T, we use this as a modifier for some tolerances, and the reason why we use maximum material condition, it provides us the most material, which allows us to assure that our parts are going to fit together. So we have tolerances, say like locational tolerances, that are defined at the maximum material condition, and then that determines that the parts will always fit together. But as the part deviates from the maximum material condition, there's going to be more clearance. Okay, so maximum material condition is a term we use a lot in GD&T to assure that the parts are going to fit. Let's talk about the 2 rules of GD&T. Rule number 1, and I'm just introducing these rules here. We're going to talk about this in future lessons, but here's where we introduce the rules. Rule number 1, perfect form is required at maximum material condition. Any dimension feature of size must have perfect form when the feature of size is at its maximum allowed by the tolerance. As a feature of size deviates from the MMC, then the feature has more room to allow for imperfect form. This goes back into using MMC as a means to guaranteeing the fit of your parts. Here's some examples. So we got a drawing required, 1 inch plus or minus 10 thousandths. Okay, so what we have here is a maximum material condition on this cylinder feature of 1 inch and 10 thousandths. Okay, and that establishes a perfect form boundary. Okay, so when the part is made at the maximum material condition, it has to be perfect because part has to fit within this perfect form boundary. Okay, now let's say we start making the part smaller. So in this particular case here, we got the part made at the minimum size tolerance. Okay, and then when it's at its minimum size tolerance, it could fit within this perfect form boundary and still allow for a little bit of bowing in the part. Okay, so this part's a little bit banana shaped, but that's permissible only because the part is at its least material condition. Now, if the part was made at its maximum material condition, like here, it has to be in perfect form to fit within this perfect form boundary. That's rule 1. Perfect form is required at MMC. So let's talk about rule 2. Rule 2 says, regardless of feature size, and that's a RFS, we abbreviate regardless of feature size, and regardless of material boundary is assumed. Okay, so what this means is that we use the MMC modifier here and here to modify the tolerances or how the tolerances are applied. And again, it's usually to allow for fits of parts. Now, in GD&T, Y14.5, if we do not specify an MMC here, which is maximum material condition, or an MMC here, which is maximum material boundary, if we don't specify those, then it automatically defaults to regardless of feature size. And again, we're going to talk about these rules in detail in the next chapters. This is a little thing about machine capability. I'm not talking about machines that produce parts. Each machine is uniquely capable. Each machining program for a part is uniquely capable. Smaller tolerances generally require larger cost. The tighter your tolerances, the more your parts are going to cost. So know your company and your supplier's capabilities, and machining handbooks provide general capabilities. So to calculate your tolerances, you need to know what the capabilities of the machines are to keep your part costs down.